Good morning, everybody. So, was the weekend that good that this number of people are gone? Where's everybody? If you're listening to this and you aren't here, shame on you.
Parking's so bad.
Is it parking?
It's worse than last week.
Really?
Yeah.
Okay, I apologize. If you're stuck in parking and you hear this later, I'm sassy. Yeah, don't skip out on class just because there's a YouTube. I am wearing my vector hat for a reason. More on that in a bit, okay? But today we take a step away from vectors. It'll happen, I promise, okay? I need to finish up just a little bit about Gauss's law, that I didn't, and then we'll get into electric potential and all that kind of stuff. So let's see, we didn't have a lab this week because yesterday was a day off. Next week's lab will be your first equipment lab. I don't know why I did air quotes, there will be equipment there. And then it's not next Thursday, but the Thursday after I think is your first exam. Right? So we have this week, next week, and then we are taking the exam. All right, so we did Gauss's law, and I know it's a little bit confusing. We're talking about flux, and let's just review flux real quick. Flux is this idea, right? Trying to capture how much flow happens through a surface. Okay? Now, in Gauss's law, these surfaces are what we call closed surfaces. So you can go ahead and just think of like a basketball spherical surface, right? And if there's a charge inside, remember those field lines start on positive charge and radiate out. So we would have flux through the imaginary basketball that surrounds a positive charge, and vice versa. So mathematically dealing with Gauss's law, and how you kind of implement, I think I gave you a homework problem where you've got to calculate an electric field or something like that, okay? Flux, and this is the symbol for flux. That's the Greek letter, capital Greek letter phi. Sub E meaning electric flux. We'll have magnetic flux later, okay? Gauss's law says that whatever that flux is, I'll show you how to calculate in a minute, that flux is always going to be equal to the charge inside your Gaussian surface, your imaginary basketball, divided by a physical constant called epsilon naught. So again, lots of Greek here, okay? Sometimes that Greek letter epsilon is printed like that, right? Like if the computer were printing it out. That can be a little bit difficult to, that looks awful lot like an E, doesn't it? So we tend to, when we write it, draw a C with a kind of a middle E bar on it, right? Just to make it look different from a C or an E, right? Epsilon naught. That's a constant, and it's got a fancy name, okay? It's called the permittivity of free space. I'm not going to hold you to that, but you'll hear me say that every once in a while. It's 8.85 times 10 to the minus 12 Coulomb squared divided by Newton meters squared. And I know this is coming out of left field. You're like, well, where did that number come from? Blah, 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 blah. But when epsilon naught is around, you're going to see epsilon naught a lot in this class. Epsilon naught is a fundamental constant of our universe. In other words, this never changes, no matter where you go. And it's responsible for setting the strength of the electric field. If you see epsilon naught in an equation, but you don't see electric field written anywhere in that equation, I guarantee you there's an electric field somewhere. Epsilon naught is always involved when there is an electric field around. All right, so this right here is Gauss's law. What Gauss taught us through this idea of flux was that you can calculate the electric field of something by simply knowing how much charge is on that object. And this fundamental constant. It's really quite amazing, and I'll show you how it worked here in just a second. But before I do that, we really need to tell you how to calculate flux. The flux itself can be calculated by taking the magnitude of the electric field, multiplying by the magnitude of the area that your Gaussian surface is, and then, strictly speaking, the cosine of the angle between the electric field and area vectors. what's area? A scalar or a vector? They're tearing out concrete, I don't know why, but we're gonna be interrupted every once in a while, but.
I'm assuming it's a vector.
What's area? How many of you, up until this moment, thought area was a scalar or just a number? All right. Area does have orientation. How would you find the area of this binder? Just the top cover of this binder. Right? Just do the height, the width, done, right? Okay? But the area that you see right now can change with orientation. How much of the front cover do you see now? Much less. So the apparent area changed. Now you're like, well, the actual area didn't change. But the orientation of the surface did. And so the area vector, the direction of the area vector is perpendicular to the surface. Okay? So for this binder, I can rotate this area in a bunch of different ways and communicate in ways that I never could if I just knew so many square meters, right? I can tell you so many square meters with a certain orientation. So areas are vectors, and I'm pretty sure you never knew that or were taught that until this moment. Don't panic though, okay? We usually, almost always in physics 2B, make sure that the angle between the area and the flux that we're trying to measure is always 0. And what's the cosine of 0? 1, okay? So we very typically just write the flux as the electric field times the area. So let's use Gauss's law to find the electric field of a point charge, okay? So here's a charge. What you want to do is you want to draw like an imaginary Gaussian surface around it. It's going to be a basketball, okay? And we say we're going to put Q inside of it, okay? Inside that imaginary surface, and we're going to use Gauss's law to calculate the electric field of this point charge. So I need to take the flux and set it equal to the amount of charge I have inside my Gaussian surface divided by this weird constant. Well, that flux is going to be E times A equals Q inside over epsilon naught. And this thing right here, it's hard to tell, but this is a three-dimensional sphere. So we need the surface area of a sphere. Does anybody remember the surface area of spheres? No, nobody remembers that, right? Except annoying physics teachers, right? It's 4 pi r squared. That's the surface area of a sphere. So we take 4 pi r squared. The charge we have inside is Q, and we have this thing epsilon naught. We solve for the electric field. It's Q over 4 pi epsilon naught times r squared. And I'm trying to tell you that that is the electric field of a single charge in space according to Gauss's law. But that doesn't look anything like what we had before, right? The electric field of a point charge was what? So what's K? It's 1 over 4 pi epsilon naught. That constant that we've been giving you, that we use a lot, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared, is 1 over 4 pi epsilon naught. That is the very first molecule on the top of the iceberg that is Gauss's law. Gauss's law is exceedingly powerful. You should be thankful that you don't have to experience the entire iceberg, okay? However, Gauss's law is something I came to know and love because it saved my bacon over and over again. When something is really hard, like you've got really weird charge distributions, Gauss's law can actually save you hours of time. in calculating electric field vectors. It involves vectors in the sense that there's electric field and area, but you notice how I never wrote down any vector sign over here? This flux is a scalar. It ends up removing vectors if you're clever. The hard part is being clever about it, okay? And convincing your teacher that you were sufficiently clever, right? But we saved multiple hours of time in graduate school. There were times I got to go home and see my wife because of Gauss's law. So it's always good in my book. Anyway, I just kind of wanted you to see how to calculate a flux and use it to do point charge. I think you got more or less the same problem on your homework. And hopefully that will help. All right. Let's take another step. Okay? The stuff I've been teaching you is hard, right? Forces, electric fields, a lot of times you're just sort of hanging on for the ride, okay? Letting it go in one ear and out the other. And that's okay, right? But you do need to show some ability to work with it. But it would be nice if there was something that we could hold on to in electricity that didn't involve vectors. I mean, let's be honest, right? It's the vectors that are causing problems, isn't it? All these directions, components, having to calculate, right? Break things up into components, add things together, right? If we could just get rid of the vector part, maybe, just maybe, I could understand what was going on. Well, good news for you is I can take the hat off now. So I'm going to introduce you to an idea that gets rid of the vectors. And it's an idea that you've already experienced, believe it or not. It's something that a lot of everybody talks about and doesn't know what they're talking about. Is my hair nice and messed up now? Okay, go. My kids call it physics hair. It's common in talking about, but people don't understand fully what's going on. And it's analogous to something you've already experienced in physics 2A. And I know, I just mentioned 2A and you're all in panic and PTSD or whatever, right, okay? I'm gonna ask you to remember something from physics 2A. But it's okay, I'm here with you, hold your hand, and be all right, okay? Because in physics 2A, you did this. We did chapters 4 and 5. Is it nasty of me to bring up Newton's laws and free body diagrams and all that kind of stuff? Remember how bad that was, right? Okay. And after we did Newton's laws, we did energy. Did energy have vectors in it? Not really. There were little ones kind of hiding in there. But we did something called a dot product that would get rid of our vectors, and energy was a scalar. And at the time you didn't believe me, but later on you understood energy is actually easier than dealing with Newton's laws. Some of you are willing to fight me on that. That's okay. You're allowed your opinion, okay? But we're going to do exactly the same thing now with electricity and electric fields and electric forces. We're going to develop something that is very close to the idea of energy, but in electricity. What kinds of energy were there when we talked about mechanical energy in physics 2A? Potential energy and kinetic energy, okay? And then if you're in my class, we did talk about other forms of energy, like we got the thermodynamics, we talked about thermal energy and a little bit of chemical energy and nuclear energy. We're going to get actually to all those forms of energy, but I've got to introduce you now to the one form of energy, if you remember from thermodynamics and efficiency. What was the one form of energy that was close to mechanical energy in efficiency? Like if you can convert from one to the other, do you remember? It's okay if you don't. Remember electrical energy? Going from electrical energy to mechanical energy is way more efficient, say, than going from chemical energy to mechanical energy. Yeah, there was that hierarchy. Again, I'm just trying to tie it back. I'm not going to test you or quiz you on any of that, so don't worry if you don't remember any of that. But electrical potential energy is the new idea that I've got to teach you. Okay? So let's talk about that. Let's review just a little bit of our gravitational potential energy to begin with, okay? So this ball has gravitational potential energy because it's in the Earth's gravitational field, and it has the potential to move somewhere, doesn't it? Okay, right now, it's just sitting here, but it has potential energy. If I let go of it, what happens to the potential energy? It changes into kinetic, right? Okay? So, work is the amount of force times distance that, in this case, the gravitational field is doing. Okay? So, is the work positive or negative if I drop the ball? Say it loud. Positive, okay? Force is down and direction is down, isn't it? So the work that gravity is doing is positive, but what's happening to the potential energy? Is it increasing or decreasing? It's decreasing. So, baked into the concept of energy and the kinds of energy we have and the work that's being done is this idea, or this truism, if it were, okay, that when something falls, right, has mass m in a gravitational field, it goes from a state of higher or high potential energy to low potential energy. But the work being done is positive. The force is down, and the direction it's going is down. So work and changes in potential energy are opposites of each other. If your work is positive, then your change in potential energy is negative. Vice versa. If I lift something up in a gravitational field, the work done by gravity, which way is gravity pointing? Down. Which way is the ball going? Up. That's negative work, right? So I'm working against gravity to lift this thing up, and the object's potential energy is increasing. So just a brief review, okay, of what our conservation of energy and work-energy relationships were from Physics 2A. Not going to test you on that, right? But I need to have you in that zone of thinking so that now we can talk about its electrical equivalent. And for this one, I'm going to turn it sideways. And I'm going to put a charged plate, two charged plates. One's going to be charged positively, one's going to be charged negatively. What can you tell me about the electric field that exists between these two plates? Where do electric fields start? On positive charges, and where do they end? Negative. On negative charges. An electric field, the lines of electric field, will want to take the shortest, straightest path without tangling or doing anything, right? So the electric field would just be nice and uniform and straight all the way across between those two plates. Okay, that's our field. I come in here, I grab a charge, and I plop a positive charge down right there. Knowing what you know about electric fields, knowing what you know about forces and Coulomb's law and all the stuff that we've been learning, what direction, if I let go of that charge, what direction is it going to go? To the right. Why? It's attracted to the negative and it wants to get as far away from the positive plate as possible, right? Okay? Just like a ball being let go in the Earth's gravitational field, what direction does a positive charge go when it's let go in an electric field? In whatever direction the electric field is pointing. Right? A positive charge will follow the lines of electric field. What direction is the Earth's gravitational field in this room?
Down.
Down. Right? So what direction do things fall? Down. They follow the gravitational field, right? If I want to take that positive charge and say move it closer to the positive plate, Do I have to do work on it? Yes, right? Does the electric field do work on that positive charge if I let it go? Yes, because force and distance are happening, right? So the electric field and the gravitational field are very analogous. They're almost like the same idea. It's just electric field, gravity always acts down or in, and electric fields act however they're going to act, right? Okay, so if you had to identify a place in this field where the potential energy is high, left or right hand side? It's the left, isn't it? Because that's where the charge is going to fall from, right? So I've got high potential energy over here, and I've got low potential energy over here. So far, the analogy is holding up, right? Okay. Now, it can get a little bit weird. What if the electric field were pointed up? Which way would the positive charge fall if the electric field were pointed up? Up. Right? You're like, Okay, here's where it gets worse. What happens if I put a negative charge in this field? If I plop a negative charge down, say right there, what direction is a negative charge going to go? It's going to go to the left. Negative charges go opposite the direction of the electric field. Electric field is defined by what a positive charge would do. There is no analogy in gravity for this. We do not have negative mass. If we did, if I had a ball of negative mass and I let go of it, which way would it go? Up. Okay, negative mass would fall up, positive mass would fall down. In gravity, we don't have a negative mass. Everything just attracts. But in electricity, we have both positive and negative charges. And negative charges roll uphill. How's your brain? Okay. Yeah, it's a weird thought. It's a weird idea, but it's nevertheless true. Negative charges do opposite things than what we're used to. And what's the mobile charge carrier in just about every material? Is it protons or electrons? And what are electrons, positively or negatively charged? And we blame Ben Franklin. 50-50 chance and he messed it up. And you're like, well, Mr. Balogh, why don't we just redefine the electric field, right? Make the electron positive. There's this thing called historical inertia. You think getting the United States to change to the metric system is hard? Yeah. Everything, all of our science is based on the electron being negative now. It's a bit of a pain. Okay, so I've been talking about potential energy, right? Potential energy for gravity was like mgh. It was the force times the distance. So we can actually figure out what this is, right? The work being done by the electric force, okay, is the force times the distance. Okay, so let's make, let's see, your book uses delta S for some reason. Okay, fine. This distance is delta S between the plates, okay? We're gonna find the work that the electric field does on this charge. Okay, so we need the force on this charge. If we know the electric field, how do we find the force? It's not Coulomb's law. Remember, electric fields are force divided by charge, right? So if you know the electric field and you know the charge in the electric field, you know how much force is acting on it. Force is going to be the charge times the electric field. So there's our force. Our distance is delta S. This is a lot like mg times h. This quantity right here Q times E times delta S is called the electric potential energy. Your book uses EPE. I don't like it. That's too many capital E's. I like P sub E sub E, or P, because that tells me it's potential energy, I got that. And then it's electric potential energy, okay? And that big E on the right-hand side, that is electric field, right? Again, too many capital E's flying around. And just like gravitational potential energy, this electrical potential can be turned into kinetic. You're like, where is the potential energy going to go as that positive charge moves from left to right? Well, it's going to speed up, isn't it? And so the QE delta S is going to turn into 1/2 mv squared. Just like an MGH would turn into a 1/2 mv squared. Energy is energy. But you'll notice the title of this slide is lacking a word. Energy. In electricity, we take it one step further. And we eliminate the term energy and instead talk about electric potential. What is that? You take your electric potential energy and you divide out the charge that's experiencing that electric potential energy, and you're left with something called the electric potential. The symbol we use for electric potential is V, capital V. And you know it as voltage. Where have you heard of volts before? Batteries, right? Getting shocked. What comes out of the wall? What's the voltage of this wall plug? 120. 120 watts. You don't know that?
No.
Between 110 and 120 volts? You don't read the little bricks? Right? Okay. This little brick plugs into the wall and then makes your laptop go? What, is it juice flowing in here? What's going on? The answer is sort of yes. So, that's electrical juice. Voltage. The voltage of a battery. A AA has how many volts? Nobody knows. Nobody uses AA anymore, right? 1.5 volts. It's written right inside the battery.
Do you think I read? It says it right below, I think. It says like double.
Yeah, 1.5 volts. Your cell phone's battery. Here's where we get really nerdy. What does your cell phone's battery run at? 5 volts. How do I know that? Because USB, the standard, okay, assumes a 5 volt ground to positive difference for charging. Current can change, but the voltage usually stays the same. So voltage is all around us, and voltage is this sort of thing like, oh man, this thing has so many volts, it's gonna kill me. Actually, voltage never kills you. It's current. We'll talk about that when we get there, right? What are the units of electric potential? What do you get when you take a joule, a potential energy, and divide by a coulomb? I have no idea, Mr. Balogh. I'm lost. Do yourself a favor and don't try with the units. Like, I'm serious. Don't try. Just believe. Okay? A joule divided by, if you want to take a joule and turn it into a Newton times a meter, kilogram meter per minute, you'll eventually see that it will work out. But honestly, you have better things to do with your time, and that's a rabbit hole you do not want to go down. So how do you stay safe? How do you make sure your units are correct? What have I been begging you to do now for 1.1 semesters? Use standard units. Standard units in equals standard units out, right? So a joule per coulomb is equal to a volt. Symbol V. Okay? All right, so what does this mean? Okay, so first of all, we can extend this just a little bit and say, well, if we know the electric potential energy, which is QE times distance, right? And we divide that by a charge to get a voltage, what cancels out? The voltage does the same thing that electric field does for Coulomb's law. The electric field allowed us to get rid of one of the charges that's involved in feeling the force, right? And we developed this idea of the electric field. Electric fields are easier to visualize than vector fields of forces. What voltage does is it allows us to take the field and simplify it down to a single value or point that doesn't have a direction. It does have like a sign, it's positive or negative voltage, but beyond that, we don't have to worry about the directions that things are taking. And I'm going to show you how nice that is here in a second. But you do need to realize that we can get back and forth between, okay, so technically there is a minus sign. I'm just going to throw it in here. Voltage and electric field are opposites of each other. That minus sign comes about because of the work potential energy relationship I was talking about earlier. You don't need to worry about it too much. But they are kind of opposites each other. But if I know my voltage, and I know how my voltage changes, you see how there's that delta distance in there, that delta S? If I go from one point in space to another point in space, and I understand if my voltage goes up or down, I can tell you everything you need to know about the electric field. It's really quite amazing that you can pull information about electric field out of just a couple of numbers. Now, a lot of what I've been doing in here is conceptual, esoteric, kind of, high-level thinking. And what I need to do is I need to get into showing you how this works in a practical way. But I do want to show you a video, an animation that tries to help with conceptualizing and visualizing what the voltage is doing, okay? The video is going to show a stick figure riding on a bike, okay? And it's going to go up and down hills. Voltage is very much like going up hills and going down into valleys, electrically speaking. And we'll see if we can't convince you of that here in a second. The bicycle, the stick figure is going to have a red head, like just a red sphere for a head. That's a positive charge.
By the same token, the contours on this map give a clear representation of an electric field. These are contours of constant electric potential. And they too represent a terrain that has its ups and downs. When real ground goes up and down, the prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential. Moving up the incline of potential is hard work. And
Really
the steeper
hard.
it is, the harder it is to climb.
Sucks to be him, huh?
Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope.
Okay, so the video introduces this idea, this analogy, right? Okay, that electric potential is elevation. So a mountain's got lots of elevation, right? So electrically speaking, a mountain would have lots of electric potential. The slope, the way that you would ski down the mountain, would be the direction that the electric field points. Where does electric field point? From high up in the mountains down to the valleys, right? okay? So electrically speaking, positive charges roll downhill. They follow the curve of potential. They follow the terrain, okay? What do negative charges do? They go the opposite direction, okay? They roll uphill. But voltage, when somebody tells me that there's something's at high voltage, I'm thinking of, okay, electrically speaking, right, it's a mountain, right? And charge is going to want to come from that mountain down, either to where I am, or if I'm standing on the summit of the mountain, right, away from me. But did you catch what happens when the electric potential is staying the same? When that bicycle rider got to the top and was on the level, was the potential zero up there? Or was the bicycle rider on the top of the mountain? They're on the top, right? So the potential wasn't zero. It just wasn't changing. And so how much electric field do you have if the potential doesn't change? What was it? Zero. If your potential's the same everywhere, that means you're on a mesa. You're on a flat mountaintop. And if you put a basketball on a flat mountaintop, is it going to roll anywhere? No. So why is it safe to stay in your car during a lightning storm, or if an electrical wire has fallen across your car and your car is at 20,000 volts? Well, why is the electric field inside zero? Every part of your car is at 20,000 volts. So what's the difference between, say, the seat over there and the seat over here? To see, that seat's at 20 and this is at 20, what's the difference in potential? It's zero, so how much electric field is going to exist? Zero. And remember, it's electric field that gets charges moving, and it's moving charge that kills you. So why is it that birds can land on wires and not die? They land on the 20, 30,000 volt lines all the time. 1 foot is at 20,000 volts on the wire, and the other foot's at 20,000 volts on the wire. What's the potential difference? It's zero. How much electric field? Zero. How much force? How much current? 0, 0, 0. Bird is safe. The sad part is that when I was, I helped go work in the summer at my grandfather's farm, is we would often find eagles and owls that had been killed by electrocution from the power lines that ran around the farm, okay? But the sparrows and the robins and everything else, the starlings that were landing on those lines were always fine. What was the difference? Size of the bird, right? But an eagle or an owl comes and tries to land on a power line, there's a good chance with that 4+ foot wingspan that the one wing's going to touch the positive 20,000 and the other one's going to touch the ground or zero. There's 2 lines in order for flow to happen, okay? And so now, right, if that owl has got a wing at 20,000 and another wing at 0, is there a potential difference? Yeah, okay? Big mountain over here, big valley over here. And which way is all the charge going to flow? So you don't get out of your car if it's charged at 20,000, because if you try to step out of your car that's at 20,000 volts and the ground's at 0, you now become the conductor between those 2 points. All right, with that morbid thought, let's do a quiz.
Mr. Balogh?
What?
That one's kinetic energy. Why you write it with Q?
Well, this is kinetic. Potential energy has to be converted into kinetic energy. That's the kinetic energy side. This is the potential energy side. Okay, so using this in a practical way, right? Right there, okay? So we're going to not show you where this comes from. I'm just going to give it to you, okay? The voltage, the electric potential from a point charge. So charges cause electric potential just like they cause electric fields, is equal to KQ over R. This looks very similar to what? You remember electric field? KQ over R squared. But electric field was a vector. It had direction. The electric potential does not. It's just a number. And this is the electric potential of a point charge. So like a positive charge sitting here in space, okay? We can find the electric potential at that point, or at that point, or at that point. And all it is a number. Now, what do you think the electric potential might be the closer you get to a positive charge? Bigger or smaller? It's going to be bigger. Because the distance r is going to be smaller. Where does r show up? Numerator or denominator? It's in the denominator, right? So the closer you are to a charged object, the higher the voltage is going to be. Further away from that charged object, the less the voltage is going to be. And we can use this concept and idea of voltages to pull off problems that, well, involved a lot of vectors before, but don't anymore. So what we're going to do, you remember, so we did a problem with the electric field where we found the electric field at the origin, okay? So what we're going to do, okay, is instead we're going to find the electric potential at the origin. We got two charges. They're causing electric potential to happen. And we want to find, we're being asked, oh darn it, come back here. Here we go. We're being asked to find the electric potential right there. Do we have to draw a vector diagram? No. Why not? Electric potential is not a vector. If I want to find the electric potential at the origin, the voltage at the origin, all I need to know is what the voltage is from charge 1 and the voltage is from charge 2 at that location. The voltage due to charge number 1 is K times Q1 over the distance that the charge is at. That's 8.99 times 10 to the 9. And now it becomes very important that you include the sign. So with electric field, we didn't do signs, right? We just did magnitudes and we took care of the vectors by drawing pictures. With voltage, you want to use the sign on the chart. It's very important. So I am going to put in negative 3.5 times 10 to the minus 6 because it's a negative charge. I'm going to divide that by the half meter. Why am I using meters? Standard units in equals standard units out, right? And I'm guaranteed that this is going to come out in volts. What I get here what I get here is negative 63 volts. And then I do the same thing for charge number 2. Okay, Q2 over the distance to 2, 8.99 times 10 to the 9. The charge here is 5 times 10 to the minus 6. And my distance is 0.25 meters. My biggest problem is that I always want to square what goes in the denominator. So when you're trying to troubleshoot and you don't know why y plus is giving you the red box of doom, right? Go back and check your denominators, right? Make sure you didn't square things where you didn't intend to, right? Squared for electric fields, not squared for electric potentials. And this turns out to be 180 volts. And so that means the voltage at the origin is going to be the combination of those two voltages, which is 117 volts. I know you might be, well, you probably don't want to, but you might be asking, well, why would I do this? Right? Fair question. But let's just stop right now and compare and contrast this with what happened last Thursday with the electric field. Not only did we have to find the magnitudes of the electric field, we then had to go figure out their directions, positive x, positive y, and then we had to do Pythagorean and inverse tangents and vector add everything together. None of that happened here, right? Okay? Voltage is a straight up number. Yes, it can be positive or negative, but we just put it together, right? We add negative, whatever, add positive, and we come up with this value for what the voltage is there. Okay, now I know the voltage there. Can I find the electric field at that point? Well, sure, there's a relationship between the electric field and the potential. And once I have the electric field, can I find the force? Absolutely, right? Because once I know that, so the reason that we're going to spend actually the rest of this unit talking about electric potential is not only is it not a vector, and it's kind of handy that way, it's the thing we can actually measure with our instruments. There's no such thing as an electric fieldometer. I mean, you can go online and buy an electric field meter, but it's not measuring electric field directly. What it is measuring is electric potential directly. Voltage is something we can measure directly with our multimeters. And so what an electric field meter does is it simply converts for you, right, into electric field. But the actual measurement is being done with electric potential, because it's easier to figure out what the electric potential of a charge is than to figure out the field that it's actually sitting in. And so to move in that direction of using the concept and idea of electric potential, I want to really drive home the relationship between electric potential and electric fields conceptually. Let's see, what's next Monday's lab? Your teacher should know, we should ask him. 2B. Okay, so lab 3, which of course I didn't write down at all. Yeah, okay, so next week's lab is going to be all about working with charges and how do you know when something's positive and negatively charged, and how do you tell the difference? And you're gonna end up doing a similar thing to it, where you're gonna end up in a similar situation that Ben Franklin was in, where you're gonna have to argue about what's positive and what's negative. The lab after that, you're going to be working directly with voltage and electric field. That lab has no math in it. It is all pictures. So if you've been sitting here the entire time in your physics career going, when is my moment? That I could just do art, right, and excel in this whole thing, that's your day. Because you need to bring crayons for that lab. So not this coming Monday, but the Monday after.
Really?
Yes. So like, just at least 2 different colors. So pencils, crayons, 2 different highlighters, black and blue ink, I don't care, but it needs to be 2 different colors. Not next week, but the week after. Students come out of this lab going, 1 or 2 students, oh, this is the best lab ever, or I can't believe you made me draw something. Anyway, I wanted to make sure I had the labs straight in my head for what's going on. The holiday always messes up the spring schedule. Okay, so the connection between electric fields and electric potential. These are pictures right here of electric fields. Two different situations, right? The one on the left I've shown you already today. What is that? Where did we see that one before? It was the 2 parallel plates, right? And so by looking at this field, we can say, we know where positive charge is. Positive charge is somewhere over here, right? Now maybe it's a physical plate, maybe it's out in infinity, it doesn't matter. We know that's the positive side, and we know that the negative side is like over here, right? Just again, because of the rules of field lines and all that kind of stuff, okay? Same thing with the drawing on the right, okay? What charge is sitting right there at the center of all those electric field vectors? It's a negative charge, and you know that right away because you know that electric fields point towards negative charges. There's a negative charge sitting in there, which implies again that there's positive charges all the way around out here, probably uniformly distributed, and I'm not drawing them very uniformly distributed. Okay, so we can draw lines of equal potential. We shorten that to equipotentials. You'll hear that word in the book and online and all kinds of places. But a surface, a line, something you can picture where everywhere along that line, the potential is the same. Now remember that potential goes as the inverse of the distance, right? And so so charge staying the same, K being a constant, the only other thing that can vary is distance. So in order for the potential to be the same, what must be the same? Distance. For the drawing on the right, what would the line of equal potential look like for that charge? We have to keep the same distance from the charge. So what would the path look like? Complete path that is equal distant all the way around that charge. It's a circle or sphere, right? Okay. So if I wanted to draw a line of equal potential around this charge, and I started here, I'd have to keep my distance the same all the way around and have a circle. I don't know what that voltage is, it's a number, but I know everywhere along that circle, that number is the same. And the same thing about this circle right here. Ooh, that circle went. That, everywhere along that line was the same voltage. What about out here? It's getting worse. Everywhere along that circle, the voltage is exactly the same. So let's go to the drawing on the left. How do I draw something that has equal potential everywhere in that field? What is it going to look like? It's just going to look like a line, a vertical line, because we have to maintain the same distance from the charges, right? And then another one. And then another one, so on and so forth, all the way through that field. Those lines are lines of equal potential. Again, we shorten that to equipotential. This could be the 5-volt line, 4-volt line, 3-volt line, 2-volt line. I don't know what the numbers are, but what I do know is that the voltage is going down. And how do I know that? Where's the voltage high? At positive charges, right? Positive charges are mountains. Negative charges are valleys. So the voltage is going to go down. In a similar way, I know if this is a 4-volt, this is probably a 3-volt, and then a 2-volt. How do I know the trend for these equipotentials? What's sitting in the middle of that diagram? Negative charge. And what are negative charges? They're valleys, right? The voltage has to decrease as I get towards that valley. What's something you notice about every electric field line and every equipotential line I've drawn in this diagram? Be gentle with my supposed circle. Yeah, okay, so the equipotentials are the same, but like compare the black electric field lines with the green and red equipotential line. They're always perpendicular to each other. They are always perpendicular to each other. Electric field lines and lines of equal potential are always perpendicular to each other.
Because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equipotential at every point. And that's how it assumes its familiar shape.
Okay, so those field lines, right, follow kind of that curve, right? Now, granted, this drawing is a little bit of a lie because electric field lines exist everywhere in space, right? And they're kind of keeping them flattened into this plane. But I do want to show you something else, something that I hope you've seen in your life. And I mean that in more ways than one. Okay. On one level, I do hope that you have seen a map at some point in your life, right? Okay. Now, this is a very special kind of map. Does anybody recognize what kind of map this is? It's a topographical map, okay? In the days before Google Earth, right, okay, you got a flat piece of paper map, and the way the map was drawn and the information that was on it would convey information about changes in elevation. That's what a topographical map does. To a person that knows how to read a topographical map, you can see in 3 dimensions what's taking place, even though you only have a 2-dimensional piece of paper to do it with. The other meaning of I hope you've seen this is that this is a topographical map of Yosemite Valley. And I hope that you've had an opportunity to go to one of my favorite places in the universe. Okay? But I wanted to show you this map because there are lines on this map of equal elevation. Does anybody know what color the lines of equal elevation are? I see black lines, those are the roads. I see brown lines, and I see blue lines. What are the blue lines? They're rivers and streams, things like that, right? Okay. And then there's the brownish, reddish lines, okay? The brownish, reddish lines are lines of equal elevation. That means that every line, if you're on that line, and you're walking along that line, you are neither going up nor down in elevation. Okay, let me clear something. There are not literally brown painted lines out in the wilderness, okay? Right? But if this were a hill, right? Okay, if we were sloping that, the top of the mountain's up there, and the valley's down there, and I wanted to walk along a line where I wasn't changing my elevation, which way would I walk? Would I point downhill? No, because I changed my elevation. Would I point uphill? No, I would walk perpendicular to the direction of the slope, right? Any of you who are in calculus might have learned about the gradient. Okay? No? Okay, it's coming. Okay, right? But I would walk perpendicular to the slope, right? That would allow me to follow a line of equal elevation. So why am I teaching you about this? Well, in reading this map right here, I can tell you where the steep bits are. Where would the steep bits be? Where the lines of equal elevation are close together. If each one of those lines represents the same height above sea level, and the next line that represents in this case, I believe this is a 300-foot difference between lines, okay? That means from line to line there's a 300-foot vertical difference, right? And so lines that get packed together really close means that it's really steep. And lines that are spread out means it's not as steep. So here at McGurk Meadow, one of Yosemite's best kept secrets. You want to go? I can take you. Okay? McGurk Meadow, nice and flat, right? Okay? But then you get towards the edge of the valley, okay, and you get that 3,000-foot drop, right, into the valley. You can read information about how fast the elevation is going to change if you understand that those brown lines, when they get close together, means things are happening quickly. Notice that the blue lines are always what when compared to the brown lines? Perpendicular. That's a very complicated way of saying water flows downhill. So in this analogy, the lines, the brown lines of equal elevation, are the lines of equal electric potential. And the blue lines would be the electric field. So the electric field is like the waterfalls, okay, and the rivers flowing downhill. And the lines of equal potential give us a map. We can develop an electrical map of what charges are doing in a cell, in a radio, wherever the charge is and whatever it's doing, we can map out its lines of equal potential. And as soon as we know that, we know the electric field, we know the direction it's pointing, we know what force is going to act on it, all that kind of stuff. It's like a key that unlocks this. Now, you can go in and the USGS does publish their digital maps, okay, as three-dimensional rasters. So it can be very difficult looking at this to see whether or not it's going up or down unless you really look at the numbers very carefully, okay? But here, when they've overlaid the three-dimensional Earth data, right, for on top of this map, you can see, right, that's a valley, okay? It's all going downhill like that, okay? So modern mapping does have, and I know this is very low res, that's because they wanted to charge me lots of money for the high res versions and I didn't want to pay for it, okay? But having topographical maps can really save your bacon when you're in the wilderness. We will, back in the day when I was in search and rescue, we were, oh, by the way, get your quiz sheets out. Don't get your quiz sheets out, we're done with class. I'll do the quiz next time. Back in the day when I was in search and rescue, they were implementing GPS. GPS was coming online to help us track each other in the wilderness, right? To this day, they still bring paper maps. It's still packed in the bag because you never know when your GPS receiver is going to go out. All right, I will see you. Not tomorrow, but we're supposed to turn in labs. Sure. Pass your labs forward if you got them. We got 2 minutes. Pass them up the roads and I'll collect them up here. Okay. Hang out for just a little bit. I gotta ask you a question.